Okay, Assalamualaikum. Good morning. Can you hear me? Okay. How are you today? Okay, Alhamdulillah. Okay, today we're gonna move on to our next topic, which is solar cells. So this is gonna be our first lecture for device after your presentation. So basically, you have learned already a few things about solar cells. So this is actually uh to enforce your enhance your understanding, actually to enhance your understanding on what we have learned and we've discussed before, at least through the video presentations and through Q&A sessions from some of you. Okay, so we're going to look at solar cells as one of the devices which adopts p-n junction for operation. Okay, so this is the outline of our discussion. So I'm going to go through a brief introduction on solar cell, and we're going to revisit the physics of solar cells, some which we've discussed some of the fundamentals when we talk about illumination of p-n junction. Okay, so we're going to go through a solar cell operation. I'm going to go through PV technologies, uh, just like what we've covered in the presentation session, where we've seen that we have crystalline silicon solar cells, and we have some other thin film technologies like cadmium telluride, gallium arsenide, um, CIGS and stuff, right? I'm going to go through PV manufacturing as well for you to understand what's going on in the manufacturing of solar cell and what do we have in Malaysia, for you to appreciate further. And then some of the emerging solar cell technologies in recent years. All right, introduction. You can see there in 1 hour, the amount of power from the sun that we receive on the earth is more than the entire world consumes in a year. So that's actually how much power do we receive from the sun in every single hour. So it's a matter of harvesting the power. So we are still now limited by few limitations of our PV technologies. We're gonna see later on as we go through the topic. And but in terms of the incident power that we receive from the sun every single hour is that much, right? We can actually, if we can manage to harvest 100% from the incident power, so the total power available will be more than enough to power the entire world for 1 year. Okay, all right. So what is PV? What is photovoltaic? Photovoltaic is a process where we convert incident light to electrical energy, right? We've discussed last time during presentation. You can also read from here. PV cell get their name from the process of converting sunlight, which is photons, into electricity, and voltage generated from the solar cell is called PV effect, right? Photovoltaic. So the photo is from photons, and the voltaic is the effect where voltage is generated across the solar cell upon the conversion process. So it historically it originated from back in 1839, where a French a scientist, Becquerel, discovered that the sun can produce electrical charges. Okay, this is the first demonstration or first finding demonstrated by the scientists. So only if you look at the date there, 1839 until 1954, where the first practical solar cell is demonstrated. So it's a long time for the scientists back then to understand what's going on and to manage to demonstrate the first working cell. So which was demonstrated in Bell Lab back in 1954, right? And then this one is from the information is from NREL, National Renewable Energy Lab in Colorado in the USA. So you can even read there. Nobody can embargo sunlight. Embargo sunlight. Oh, what does it mean by embargo? Do you know what is embargo? Ada siapa tahu? What's the meaning of embargo? Nobody can embargo sunlight. What is embargo? What do you think? Anybody knows? No idea. Embargo means keep it away. So maksudnya tak boleh trap. Yes, more or less yes. Maksudnya kita tak boleh nak halang matahari daripada buat kerja dia lah. So you cannot keep the sunlight. So the sunlight will always be there as long as the sun is there. So we will never be out of the sun forever sampailah masanya bila kita hilang matahari satu masa nanti. But as for now, we have the sunlight daytime. We don't have the sunlight nighttime. So, but it's gonna go on forever until the time comes. Okay, until the time comes. So we cannot embargo the sunlight. It will always be there for us to take advantage from. Okay, the first modern silicon solar cell and back in 1954 generated 6% of conversion efficiency is based on silicon solar cell. You can see the journal published there back in 1954 in Journal of Applied Physics by Chapin, Fuller, and Person, entitled "A New Silicon PN Junction Photocell for Converting Solar Radiation into Electrical Power." So if you still recall the structure of solar cell that we've discussed during our presentation one few days ago. So it's basically a PN junction. So but if you look at this early structure back in 1954, it's a very simple structure made of a PN junction. So the wafer used there is N-type in the middle. So the wafer used is in the middle. Kat tengah ni is N-type wafer. And then the silicon wafer is wrapped with a P-type emitter. So this is called emitter, P-type emitter, which wrap the whole silicons. This the whole thing is all silicon. Okay, so right, so it's a very simple structure back then in 1954, and it's already generating 6% of conversion. So that means when we say it's 6% of conversion efficiency, so that means, for example, if you have an incident power of 1000 watts, for example, per meter square, so out of the same area you can actually generate a 60 watt. So, or in other words, if you receive 100 watt on your cell, so you can actually convert the incident light into 6 watt of the electrical energy, right? So that is what is meant by a 6% conversion efficiency. So simple structure back in 1954. So why PV? So why do we use solar cell? Firstly, because sunlight is abundant, we're gonna have sunlight forever until the doomsday, sampai hari kiamat lah. Kalau kita Muslim, kita percaya sampai hari kiamat. Waktu tu kita akan hilang semua benda. Okay, so until then, the sunlight will always be around, right? So then it's also a clean energy source. There's no CO2. There's no emission of any sort. There's no CO2 pollution. So, and the technology gets more efficient as the time goes on. So uh, the first demonstration back in 1954 was with 6% efficiency, and later on we're going to see that if you talk about silicon, it has gone up to about 26 to 27% for a single junction solar cell. So even though it takes quite a long time from 1950s to now 2020 to only reach about 26 27%, there's a reason for that, right? There's a reason for that. So along with the improvement in the conversion efficiency, the reduction in the technology cost will happen as well. So when we talk about technology cost in solar cell, we normally talk about dollar per watt, right? Kita pakai USD per watt. So it's how much you spend to fabricate the cell over how much power can you harvest from the cell. So therefore, it's it's defined as dollar per watt or USD per watt. Okay. If you look at the figure on the right, it's this is our incident spectrum from the sunlight that we normally see every day, right? We normally see every day. So this is the incident spectrum. Kadang-kadang kita tengok sunlight, kita tak pernah, maybe you have never seen this spectrum before. Pernah tengok ke spectrum ni sebelum ni? Pernah ada discuss in any previous courses about the light spectrum? Pernah tengok? Pernah, right. Okay then. So this is the incident spectrum that we normally get from sunlight every day. Okay. So it consists of a UV portion. Oh, sorry. So it consists of UV portion, visible, and infrared. So UV is in the short wavelength region, visible is in the middle region, and above 800 is infrared, right? Near infrared, mid infrared, and far infrared, right? From left to the right. So when you have your solar cell and you measure your IV curve and you get your conversion efficiency, if you want to compare the performance of your solar cells with other researcher solar cells, you have to compare using the very same standard test condition. So it is called STC, or standard test condition, where scientists normally use to compare the performance of the solar cells. So bila you ada solar cell, if you measured under the same calibrated condition, then only you can compare with other solar cells performance. And this is especially needed when you want to declare a new world record for your solar cell. So you kena buat measurement ni under AM 1.5 solar spectrum. AM means AMS. AMS ni you can see later on PVC-DROM website. Is actually related to the optical path that has to be passed through by the incident sunlight before reaching the cell. So the incident power is 1000 watt per meter square. So that means to be able to do the measurement, you have to use 1000 watt per meter square of incident power, and then the measurement has to be done at 25 degrees C. Then only it will fulfill STC, or standard test condition. Kalau you buat you punya measurement not using this condition, or maybe you are using 1.5 AM solar spectrum, but the power is not 1000 watt per meter square. Let's say you are using 500 watt per meter square, then it's already not at STC. It's not at standard test condition, right? So in that case, you cannot compare apple to apple between your cell performance to other cells performance. So it has to be done at STC. All right. Previously, we have learned that a solar cell is a PN junction device. So to be able to work, we have to have a P type, we have to have an N type material together. Then we have to have a front contact and a rear contact. So this is basically what I call a simple structure of solar cell. Let us go through one by one. What is actually in the solar cell? So all right, if you look at the layers in this picture, um all right, this one, the central region, the gray area. Oh, I need to use, hold on, I need to go to smaller. I think it's better this way. If you look at the gray area here, right, the gray area, it's p-type silicon. So that means we are starting our silicon solar cell fabrication with p-type silicon. Then you need to have, see, the next layer on the p-type silicon is the red color. The red color is given by n plus type emitter. So that means we have a pn plus junction, right? So the top layer is emitter, the red region. So the gray layer is normally called base or absorber, right? So what is the blue layer, right? The blue layer on top is the anti-reflective coating. Normally for silicon solar cell in industry, we use silicon nitride. So there's a reason for that. The main reason of us using silicon nitride is actually due to its refractive index. So the refractive index of the silicon nitride is 2.0, about 2.0, n is equal to 2.0. Okay, right. Before you see the silicon nitride, you can actually see a rough surface, right? So the surface is not so flat, so it's actually composed of front pyramids in order to scatter incident light from the sunlight. Let's say sunlight is here, and you have all the incident light on the front side. So the front surface pyramids will help to scatter the light into multiple directions to improve light absorption in the silicon solar cell. So on the front side, we also have metal contact. This is usually Ag or silver. So it will form fingers. So that means when I say fingers, that means it doesn't cover the surface fully, because we don't want to block the incident light from reaching our PN junction. So we have to therefore coat the surface with fingers of silver. So that means there is space in between, so that you can have sunlight in between to hit your junction to generate electron hole pairs. Right, on the rear side, we have a dielectric layer and local BSF. This BSF is actually called back surface field. Kita ada discuss dalam presentation baru ni. Back surface field. Right, what is this BSF? Briefly, it's if you have a p-type wafer, then your BSF has to be p plus or p plus plus. So it's actually a form of junction as well. So it's just that the junction is not of opposite polarity. So dear, we call it low high junction, p plus or p plus plus. So what it will do is that it will minimize a rear surface recombination, right? Rear surface recombination. It will actually repel electrons away from the rear surface from recombining with holes and causing loss of carriers. So that's why we have it there. So we also have a dielectric layer. Dielectric usually made of silicon oxide and also silicon nitride. We're gonna see why later on, but briefly, it's there to do surface preservation for your back surface, right? It's called surface preservation. Tadi kita dah belajar kan surface preservation. We want to preserve all dangling bonds and make sure recombination is minimized. Okay, so that's the basic structure of our solar cell. So this is the operation of solar cell. We've discussed a couple of times already. So to be able to work as a solar cell, the solar cell has to absorb the incident light, and to be able to absorb the incident light, the photons energy from the sunlight has to be more than or equal to the band gap, right? Band gap energy, or EG. So for the case of silicon, So the EPH has to be more than 1.12, right? EPH has to be more than 1.12 for us to have photo generation process in the solar cell. So what's going to happen if the photon energy is less than 1.12? What's going to happen to the photons? Last time we've learned, right? So what happens to the photons if the EPH is less than the EG? What's going to happen to the incident light? Anyone? What happens to the photons? Are they going to get absorbed? Okay, what happens to the photons with energy less than 1.12? So yeah, they're not going to get absorbed, right? Because the energy is not enough to knock out the valence electrons. So if the energy is not enough, what happens to the photons? Kemana photon tu? For example, if you look at this sunlight and there are photons in the sunlight, so it hits the solar cell. So if the EPH is less than EG, what happens to the light? Apa jadi dekat sunlight tu, ke photon tu? It's not absorbed, so what happens? It's gonna get, what is this? Do not pass through the, yes, less absorbance. Do not pass through the band, scatter away. The answer is, the photons are going to get transmitted through the solar cell. They can leak dekat belakang solar cell because it's not absorbed. So when the EPH is less than the EG, you're going to have transmission loss. So that means, if you can recall last time, we've discussed that high energy photons are going to get absorbed near the surface, middle energy photons are going to absorb in the bulk, and low energy photons are going to absorb at the back. But if the EPH is not enough to knock out the valence electrons, so yang long wavelength punya photon ni or low energy, dia akan just get through the solar cell without being absorbed. So kita akan dapat transmission loss, right? So for those photons which are absorbed, they will generate electron hole pairs in the solar cell. In fact, throughout the bulk, on the front side, in the emitter, in the PN junction, and in the quasi-neutral region as well. So then we're going to have, the moment we have generated electron and hole pairs, we've learned last time when we discussed about illuminated junction, the electrons and holes are going to get separated due to the presence of electric field at the junction. So in this case, if you're talking about p-type wafer and n-type emitter, so that means electrons are going to go towards n-type and holes are going to go towards p-type. So then they're going to be collected at the metal contact on the front side and at the rear side of the solar cell. Okay, right, collection probability we've discussed already last time. So we want to make sure that our solar cell surface, both surfaces are well passivated. So that means the front side of the cell has to be well passivated, the rear side of the cell has to be well passivated to be able to ensure a high collection of carriers at the surface. Okay, so if you talk about carrier collection, you cannot miss quantum efficiency. So quantum efficiency ni kita tak pernah cover lagi. Quantum efficiency, quantum efficiency is actually, you can actually calculate this, and it actually reflects number of collected carriers or electron hole pairs over number of incident photons. So that will give quantum efficiency of the solar cell. So again, QE is the number of collected carriers, electron hole pairs, over a number of incident photons. Maksudnya kalau boleh kita nak dapat, if you have one photon incident on your solar cell, you want to collect one electron hole pair. So maksudnya kalau there's one incident photon incident on the solar cell and you manage to collect one electron hole pair, so that means the quantum efficiency will be equal to 1, right? That's the ideal case, right? In normal cases, you can see here, you can see the curve here. External quantum efficiency is on the y-axis, and the wavelength is on the x-axis. Normally, we have to see from about 300 to maybe around 1200 nanometer, right? So this is the ideal case of quantum efficiency. You want to collect everything. So you can actually calculate the quantum efficiency at every single wavelength. So katalah kalau you measure quantum efficiency ni, you can measure at 300, 301, 302, 303 step 1 nanometer wavelength up to 1200 nanometer. We don't have this QE system in our lab though, but if you want to measure, that's how it can be measured. So it has to be by wavelength. So that means you need to have your QE at this point, 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 up to 1200. So the moment you've got your QE results, you can plot, and typically it will look something like this. Curve yang ada ni, right? So if you want to know why is it important, what does it tell you? It will tell you the probability of carrier collection per incident photon at every single wavelength. So if you want to know, if you want to relate this with performance of your solar cell, you can actually use it like this. Solar cell yang you ada ni, this is the solar cell kan? You can actually flip the solar cell to make it a cross section, or maybe you can just draw. Let me open the whiteboard. Okay, let me share the whiteboard. Okay, can you see the whiteboard now? Can you see the whiteboard? Okay, good. Right. So this is, okay, let me plot here. This is actually your EQE, external quantum efficiency against wavelength. So for example, if you measure from 300 to 1200, so let's say your curve is, like this. Okay, for example, and maybe this is, so this is 100. 100 tu maksudnya 1 lah. Kalau you nak translate into 0 to 1, then 100% is 1. So it will never reach 100. Sorry, it will never reach 100 in the actual cell. So yeah, right, something like that. Okay, so to be able to understand why does it matter, this result, okay, you can flip your solar cell. Katalah ni you have your solar cell, p-type, n-type, and you have your front contact, rear contact. You can actually flip the cell 90 degrees, anti-clockwise, so you can redraw the solar cell like this. Okay, so this is your N. Saya draw, saya ingat saya draw flip. So your PN junction is now like this. Okay, so the collection probability you can actually relate to the depth of the solar cell. So wavelength yang you ada on the x-axis ni, you can actually correlate with the depth of the solar cell. So that means, katalah this is for example, this is 500. This is possibly 800. So whatever you have in the QE results between 300 to 500 nanometer actually reflects the collection probability on the front side of your solar cell. So that means in this case, it's your N-type emitter collection probability, right? So whatever happens between, whatever results that you have between say 500 to 800 actually reflects your collection probability in the bulk ataupun di tengah-tengah solar cell. So whatever you see from 800 up to 1200 reflects collection probability at the back of the solar cell. So each region here indicates the quality of the material or quality of your device on the front side, in the bulk, and at the back, right? So if you have a reference cell blue color, katalah you ada reference cell blue color ni, you ada satu solar cell macam ni kan, blue color. Tiba-tiba you buat something on the front side, maybe you change the doping level or something on the within the emitter, then suddenly maybe you will see some improvement in the EQE on the front side. Tapi yang lain-lain semua sama je. Tapi ada improvement kat sini. So that means whatever you did on the front side in the emitter, for example, now already improve the EQE of the front side. Okay, katalah you buat something, you change the passivation layer at the back. Tadi kita discuss, kita ada silicon dioxide or silicon nitride on the rear side. For example, katalah you buat something and suddenly bila you remeasure EQE in comparison to your reference cell, kata you dapat sini, you dapat semua sama je throughout the region. Tiba-tiba kat sini drop. So this reduction is due to the passivation quality at the back side of the solar cell, right? So my point here is that you can actually use your quantum efficiency result to correlate to the quality or electronic performance of your solar cell by region, right? Front side, in the bulk, and at the back. So that's my whole point. Okay tak? Do you get that? Ada soalan on the quantum efficiency? Is it okay? Tak ada? Tak ada means okay, or perhaps you are still digesting? Tak apa, kalau ada nanti you just tell me, no problem. Okay, so let's move on to the next one. So, before that, let me just go through the description here. If you can see the QE curve here, it notes down that blue response is reduced to front surface recombination. So maksudnya blue response ni kat depan lah, short of flank region is due to front surface recombination. If you see the green region, a reduction of the overall EQE is caused by reflection and low diffusion length. So in the bulk, typically it's due to diffusion length because the carriers have to travel quite a long distance to get to the contact. And if you see the red mark here, remark, the red response is due to rear surface recombination. Macam tadi saya beritahu tadi kan, quality of the passivation and stuff, right? So it actually reflects the quality of each region in the solar cell. Right, this is the IV curve of a typical solar cell we've discussed last time during presentation. So we've also discussed this when we talk about illuminated PN junction, right? So the IV curve of a typical solar cell is given by this shape. Okay, so this intersection at the x-axis is given by VOC or open circuit voltage. The intersection on the y-axis is given by ISC or short circuit current. Okay, so the performance of the solar cell is governed by equation of a diode or diode equation. I is equal to I naught. I naught is the leakage current exponential QV over NKT. Remember what is N? Still remember what is N? Kita discuss hari itu on the illuminated junction? What is N? Can you recall what is N? Tak ingat? What is N? Ideality factor, okay? Ideality factor. Ideality factor. So still remember what is the N value of an ideal diode? Ideal diode berapa dia punya N value? Anyone? Fazira, berapa Fazira? Ideality factor of an ideal diode? Yes, N is equal to 1, right? For ideal diode, N is equal to 1. If how about the value of N if you have depletion region recombination? Apa jadi kat N? Tak ingat, right? It's okay. Ideal diode N is equal to 1. If you have depletion region recombination, then N is equals to 2. Okay. Ni ideal apa ni equivalent circuit of solar cell. So you have the light current, light generated current, you have leakage current through the diode, and then we have the load, the voltage generated across the solar cell. Okay. Right, this is the same thing, IV curve of a solar cell. So you can see the description there. ISC is the short circuit current, or it can be defined as the maximum current from a solar cell, and it occurs when the voltage across the device is 0. So that means kalau you ada solar cell, you short circuit kan dia, tak ada load across it, so you're gonna get your short circuit current. Okay, so on the other hand, VOC there, VOC on the x-axis intersection. So the VOC is the maximum voltage from a solar cell, and it occurs when the net current through the device is 0. So kalau you don't have any net current through the device, then the open circuit voltage is the floating voltage. Okay, so that's given by your VOC. So kalau you kali, if you can recall, P is equal to IV. So if you use I at every point and V at every point, you can actually calculate your power. So if you calculate your power, you're gonna get this curve, and this is called power curve, or some people call it PV curve, power voltage curve, right? So that means the amount of power generated by the solar cell at different voltages. Okay, so the power from the solar cell. If you see the shape of your PV curve, you tengok dekat ISC. How about the value of the power? Is 0. Okay, it's 0. Why is it 0? Because at that point voltage is 0, but the current is equal to ISC. So therefore ISC times 0 is 0. So at this point current is 0, but the voltage is equal to VOC. So 0 times VOC is also equals to 0. Tapi along the way in between, you're going to get some values of the power. And when you times the I and V along the IV curve, you're going to get a maximum point somewhere here or somewhere here. So this is called maximum power, or P max, right? P max. So kita tengok kat curve yang bawah ni, ISC, VOC. So P max is here, where you have to multiply your V max and I max to be able to get your P max. I max times V max equal to P max. Okay. Then you can also calculate the fill factor of the IV curve. Fill factor is the squareness of the curve. how square is the curve. So that's given by MP ni maksudnya max so it equals to I max times V max over VOC times IC. So in other words, area of A ni, rectangle ni, over area of B. Right? So that'll give you the fill factor of your solar cell. It's typically around 0.7, 0.6, 0.8. Right? So the higher the value of FF, the better the performance of the solar cell. So now we know that we can get the IC, VOC, Imax, Vmax, Pmax fill factor from the IV curve. So then we can use all these values to calculate conversion efficiency of solar cell. So efficiency or is equal to eta. We normally call it eta, right? Eta is equal to P out over P in, power output over power input, and P out is equal to this. That's a numerator. VOC times IC times fill factor over P in. P in is the maximum, is the incident power under standard test condition that we've discussed just now. 1000 watt per meter square. So P in is equal to 1000 watt per meter square. Or it is also equal to, if you want to convert this into milliwatt per cm squared, you can also use that, 100 milliwatt per cm squared. Right? So it's either in watt or milliwatt. So if you use watt, so that means it has to over m squared. If you use milliwatt, on the other hand, you have to over with a cm squared. So it depends on what sort of dimension you want to use, as long as your IC, VOC are in the same dimension. Maksudnya kalau you pakai 100 milliwatt per cm squared in the equation, that means your VOC has to be in millivolt, your IC has to be in milliamp per cm squared, right? So there you can get your conversion efficiency. So it can be 10%, kita kali 100 lah, kali 100 to be able to get your percentage, or 20% or 30%, or so on and so forth. Okay. All right. Any questions so far on the calculation of conversion efficiency and IV curve? Understood? Paham tak? Ada soalan apa? Is everything okay? All good? Tak ada soalan? Tak ada highlight means okay So far okay? Alright, that's good. So I'm just gonna stop here. We're gonna continue tomorrow with PV technologies generation 1, first gen, second gen, third gen, as presented by your friends before. So crystalline silicon, thin film silicon, amorphous cadmium telluride, and others, right? So kalau tak ada soalan, yep, that's it for today, and I'll see you tomorrow then, inshallah. Okay. Assalamualaikum and bye bye. Stay safe.